All right, well, we are talking about magnetism, which is some weird stuff. It took science a few years of careful study to figure out exactly what's going on. On Wednesday last week, we talked about magnetic sources. You can have magnetic fields created by permanent magnets. You can have magnetic fields created by currents, as in coils. Today, we're going to talk about magnetic effects, that is, results of magnetism. And it basically falls into kind of three categories. We have forces, and torques, which are really just rotational forces. If a force is an attempt to move something in the X, Y, or Z direction, a torque is an attempt to rotate something so that it is spinning or reoriented. And then we can also have induced voltages, which is what we're going to spend the next couple of weeks talking about. So this week's lab, and the first thing we're going to do, is talking about the magnetic force that exists on a moving charge. And there's a couple of different ways we write this. One way is to call it F sub B. I always call it F sub B. Is Q V times or cross B. And that is a time symbol. I just circle it so it doesn't look like an X in the middle of my formula, because there is no X in this formula. It's literally a time symbol. And it stands for a thing called the cross product. Now, we've talked about vectors since physics 1 now and then, and we've talked about the fact that a vector is a quantity with a magnitude and a direction. And all three of the vectors in this equation are quantities with a magnitude and a direction. And we've talked about a little bit of vector math, the fact that you can add and subtract vectors, and the fact that you can multiply a vector by a number. We call that scalar multiplication. That's like saying displacement is velocity times time. When you multiply by time, that's a regular multiplication because time is not a vector. We've occasionally had cases where we combine two vectors and get a number out of it, like work is force through a distance. So if you exert a force on something and it goes the direction you push it, you have given that thing energy. So if you do this to a ball, you push a ball to the right, it moves to the right, you give it energy. When you're done pushing, it's moving, it has kinetic energy. That's a different kind of product. This is a weird kind of product. It's called a cross product. And for the most part, we don't think of magnetic forces as being caused by this formula. Instead, we do it like this. So the multiplication of Q times V vector cross product with B vector is sort of equivalent to just taking the Q value, the V value, and the B value and just multiplying them as magnitudes. And then include this factor of sine theta. And what does that do? Well, I'm thinking, what does sine theta do for different thetas? So what happens if theta is equal to 0? then sine theta is 0. And to know what it means for theta to equal 0, I guess I kind of have to define theta. Theta is the angle between the velocity and the magnetic field. So it's the angle between the two vectors in the formula. I guess I could say this is theta VB. So if theta is equal to 0, that means that these two vectors don't have an angle in between them. They're pointing in the same direction. And if you have a velocity of a particle in a magnetic field in the same direction as the magnetic field, there's no force. And that's what that sine theta does for us. And the same thing is true for theta equals 180 degrees. The sine of 180 degrees is also 0. So a particle traveling exactly against a magnetic field feels no force. Wouldn't even notice there's a magnetic field. It's when theta equals 90 degrees that we have sine theta equals 1. That's when we see the maximum amount of force from the magnetic field. Now that's a formula about the magnitude of the magnetic force, but force is a vector. We have to be able to find the direction. So there's a couple of ways to do this. The most common one is called the right-hand rule. So here's how it works. I'm going to try to draw a hand. There's a thumb. And fingers. That could have been worse. And here's the connection. The magnetic force in that formula is all by itself. That's associated with the thumb. And then the next vector in that is the V. That's associated with the index finger. And the next vector is the B. That's associated with the middle finger. And then the other two fingers are just going to get tucked away. We're not going to use them. And what do we do with the right-hand rule? We form what I call the physics gang sign. So your three fingers, the thumb, index finger, and middle finger, should be pointing in three mutually perpendicular directions, like XYZ axes. In fact, they are XYZ axes. Now, one thing you have to remember is it's your index finger that sticks straight out of your hand, and it's your middle finger that gets bent, not the other way around. Right. And your thumb should also stick out perpendicular to your index finger. And basically the way you do this is usually you know 2 out of the 3 of these vectors. So you line up the corresponding fingers with the corresponding vectors and then look at where the other finger is pointing, and that's the direction of your answer. So let me draw a set of axes. So there's X, Y, and Z. And let's imagine a case of a proton, positive charge, moving in the plus y direction. And let's say we want to produce a magnetic force in the plus z direction. So we must be asking about the direction of the third vector, the b. So the magnetic force is the f sub b. The magnetic field is the plane b. So I got my three vectors. I always like to walk over and stand in front of the screen for this. So my proton's moving in the plus y direction, which is toward the top of the page. My magnetic force is in the plus z direction, which is pointing out of the page. And that makes the middle finger, the magnetic field, point toward the left. So that's our answer. Now, what I wish I could do is I wish I could draw this and then have the drawing be part of the notes, but I'm not capable of that. I wonder. Well, is that the button I wanted? That's what we described, right? Okay. So I'm logged into Google Photos there. I think I'm logged in here. See a picture from yesterday. Come on, synchronize. Ooh, here it is. All right, so now I need to, pardon me while I amuse myself with modern technology. Okay, and then I need to go into OneNote, pull up the current class, and to tell you the truth, this is a lot more work than it should be to get a picture from in front of me to in front of me. Now I have to let OneNote synchronize. No, there isn't a specific finger that's a specific axis because why won't this? Phys1402-Fall18. Phys1402-Fall18. It's like not picking up the fact that there's a new lecture. Today it's not lecture 18, by the way. It's lecture 13. There's not a specific finger that's a specific axis because we already have three vectors in our equation and they can point any three directions we want. So our hand could end up being oriented any way. But once we know 2 out of the 3, then our hand is locked into a particular orientation. So this picture is intended just as a reminder of which finger goes with which vector. Once we know which finger is which vector, then we have to fit the description with 2 out of the 3 of those fingers, such as proton in the plus y, magnetic force pointing out, which is the plus z, and then the remaining finger that we haven't defined yet is the answer we're looking for. So that was the B. Maybe if I restart OneNote, it'll notice. Am I online? Yes, I'm online. Yeah, I know. But I don't want to pull up my email account now while I'm screen sharing and capturing it on YouTube. That's why I like having a second computer. And I did effectively email it to myself. I mean, I've gotten that far. It's not showing me the current lecture. It's showing me only lecture 12. Whereas here,
did you add it to lecture 12 and then copy and paste it over?
Oh, God.
No, copy paste. No, copy.
Right.
Okay, I just added it to lecture 12 as a new page called Untitled Page. Oh, there it is.
We shall get it.
We cannot be beaten by a mere computer. We will win. All right. So there is the photo of my hand, which was doing that exact configuration. So far, so good. Wonder why this oh, now it knows there's a lecture 13. Thanks. All right, so that's the basic idea of magnetic forces. The quirks happen if there is a velocity that is not perpendicular to the magnetic field. So let's say we start with an electron that has a speed of 3 × 10⁶ meters per second at an angle of 45 degrees between the x and y axes, and magnetic field is 0.4 Tesla in the x direction. So then I like to write this as a negative charge. And there's my V. And then in the background, I'll do it in a different color. Is my B. So the right-hand rule actually works just fine with this situation because the index finger is the velocity, and then the magnetic field is pointing, the index finger is kind of diagonal. The magnetic field is pointing straight horizontal, and that makes my thumb point into the screen. Now, here's the second part of this quirk. So index up and to the right. I'm not going to take a picture of my finger again. That took too long. Middle finger rightward, and horizontal. And then the third vector is thumb is into the screen. Now, here's the quirk about this. So index finger, middle finger, thumb is into the screen or into the page. The quirk is this is a negative charge because it's an electron. So negative so we reverse the direction at the end. So that magnetic field is out of the screen. Sorry.
So we wouldn't switch hands if it's...
Well, some people like to switch hands for a negative charge. My preference is to consciously switch direction at the end. So if you do it with the left hand because it's minus charge, then you would go like that. And your thumb would point out with the page. But I have enough trouble remembering left and right, so I don't like switching hands. It just screws me up in the head.
Yeah, how do you like to flip it?
It's because of the minus sign in the Q. Because really, our math was only dealing with the V and the B part of the formula. Our right-hand rule is really just for the V and the V part. And if the Q happens to be negative, it reverses everything. Well, it reverses the force. So basically, the rule is if you have a negative charge, you have to reverse something. So my preference is to reverse the force. And the other option is to switch hands and use your left hand for a negative charge. One of the other reasons I like using the right hand for even for negative charges is because then I get to get my hand into the right hand rule configuration, however it is, and hold it still and write down my result, look at my result, look at my hand, look at the known data, look at my hand, and keep holding my hand in the same position while I write down my answers. And I'm left-handed, so that works great. Now, for you people who are right-handed, which is most people, you have to keep picking up your pencil and putting it down. And I don't know, every time you move your hand out of the right-hand rule configuration and put it back, are you sure you got it exactly where it was before? I think that's a disadvantage for right-handed people in physics. So that's my explanation as to why left-handers do better in physics. So you could use your left hand for electrons, for negative Qs. My preference is just to reverse the force. Okay, let's do another example. Well, Earth's magnetic field has approximately that value. So in what direction could we have a proton fly so that it doesn't fall due to gravity? So the first thing to think about is, what are the forces involved? So we're going to have our little plus charge here. And of course, the force of gravity is downwards. So we need force magnetic to be up. So if you're going to support something against the force of gravity, you need an upward support force. And this is a side view. Now, in order to draw the magnetic field pointing north, I need to figure out my coordinate system here. So what view do we want to draw in order to figure out all the directions, the right-hand rule directions? Do we want to use a map view where north, south, east, and west are in our drawing? Or do we want to use something similar to what we see there where we have a side view? And if we do the side view, what direction does the camera face? These are the weirdnesses of doing three-dimensional analyses. How about we do a north-facing camera? So if the camera faces north, then we can draw the magnetic field in this diagram. Because if the camera is facing north and the magnetic field points north, then the magnetic field is pointing away from the camera. So we can draw X's. So B equals north equals into the page. Yes, that's the nice part of the camera view. The camera facing north view is up and down, or still up and down. Yeah. Okay, so now we have our particle, our plus, and we want F sub B equals up. So the force is our thumb. So we need thumbs up, and then we need the magnetic field to point into the page. I think it's like that.
Yeah.
Yeah. So the proton's velocity could be to the right. So V equals right equals east. Now there's two more things I want to do with this exact example. One, how fast should it go? So we have, we want F net equals 0, which is FB minus FG. So we'll take Y components of forces, and the magnetic force is up because gravity is down, and we want them to add up to 0. So this is FB strength is FG strength. In order for two forces to cancel, they have to be equal and opposite. And then how strong is gravity? 9.8 times G, or times the mass. Yeah. And so this is mg. And on the other side, how strong is the magnetic force. That's the first equation I wrote, QVB. And we'll leave out the sine theta because the velocity and the magnetic field are perpendicular to each other. So theta is 90 degrees, sine theta is 1. We'll just leave it out. And now we can solve for anything we want. This would be V equals mg over qb equals, then we have to look up the proton mass. It's at the top of the equation sheet. It is 1.67 times 10 to the minus 27th. And then G is 9.8. And then Q is 1.6 times 10 to the minus 19th, the elementary charge. And then the B was 0.00005. So we'll just do that here. .0002 meters per second. The proton doesn't have to move that fast. And the reason for that is that gravity isn't that strong. So it doesn't take much speed in order to get a magnetic force that's stronger than gravity. So if you make the proton go this tiny, tiny little speed in the correct direction, then it will basically levitate and it will not feel the downward force due to gravity. Now, one of the weird things about this is if you take an object and move it through a magnetic field, that means that the protons experience a magnetic force in one direction. So let's say that north is into the page, and I move my hand to the east. I'm moving faster than 0.002 meters per second, which means every proton in my body experiences a downward force much stronger than gravity. But I don't really notice it, because my body's composed of just as many negative charges as positive charges. And all the negative charges, instead of feeling the upward magnetic force, they feel the opposite. They feel a downward magnetic force. And the two sets of forces, the upward magnetic forces on the protons and the downward magnetic forces on the electrons, end up canceling each other out. But if you move fast enough in a magnetic field, then you could end up tearing the electrons and the protons apart. It just takes a lot more velocity to do that than to just support against gravity. Okay, let's see. Where was I going next? Yes. So kind of closely related to that last thing we did is a device called the velocity selector. And in the velocity selector, instead of balancing a gravitational with a magnetic force, we actually balance an electric and a magnetic force. And we can do this if the three vectors involved in the situation, that's the electric field, the magnetic field, and the velocity, are all pointing the right ways. So here's the setup. We're going to have a magnetic field pointing into the page. And to make things easy, we're going to have a positive charge here with its velocity toward the top of the page. Now, the first thing we want to do is figure out the direction of the magnetic force. You got it. So the velocity's up, magnetic field is into the page, so the thumb is the forces to the left. So that's F sub B. So I'm going to put that in here in the same red color as B, just because I want to distinguish magnetic effects from electric effects. Now, my original thing I wanted to do was make these two forces cancel. So I'm going to switch over to blue. Is anybody red-blue colorblind? Okay. So I'm going to switch over to blue, and I'm going to draw in F sub E. Now, how do we make an electric force that makes a plus charge push to the right? Electric force. What's that?
Positive charge to the left.
So if we put pluses over here, it'd be repelled from the pluses.
Or you could.
And maybe we could put some minuses over here and it'd be attracted toward the minuses. We could do both. So let's build a little plate, another little plate, two sheets of metal. Sheets of metal are pretty common things. And on this one, we're going to put a couple of plus charges. And on this one, we're going to put a couple of minus charges. So in that region, in between the two plates, there is an electric field pointing away from the pluses towards the minuses. So that is E equals right. So we've basically hammered out the directions of the fields that are involved. The magnetic field, if it's pointing into the screen, has to be paired with an electric field that's pointing to the right in order to allow for our particles to head in the y direction, straight up toward the top of the page. Now we just have to figure out the strength of the corresponding fields. And that comes from the electric force equaling the magnetic force. In order to get two forces to cancel, they have to be equal and opposite. So let's make their strengths equal. So this is QE is equal to QVB, and the Q's cancel, and we get E equals VB. So if the relationship between the electric and the magnetic field obeys that equation, then our particles will feel zero force. What happens if the velocity is too fast? So you build your electric field, you build your magnetic field, they have given values. You throw your particles in there, but they're too fast. which force gets stronger if the velocity is too fast? The magnetic force would get stronger. So then this red arrow for the magnetic force would be stronger, and the particles would bend to the left. And the same argument applies if the velocity is too slow. Then the magnetic force would get weaker, and the electric force would win, and the beam would bend to the right. So it's only for the particles that have just the right V that they feel zero force, and they go straight through. So then we go up here, and we build another little wall with a hole in it. And the particles that are going too fast hit the left-hand portion of the wall. The particles that are going too slow hit the right-hand portion of the wall. And the particles that are going just the right speed go through the hole and go out the other side. And we can send them on to the next piece of equipment. And at this point, we know that all the particles that go through have just the right velocity, according to this equation. And that's why we call this device a velocity selector. So the ones with just the right velocity have been selected. Now this is kind of useful in a certain kind of device. Sometimes you can make your particles go real fast in a very controlled manner. That's what this lab this week is about. You set an accelerating voltage, which gives your electrons a particular velocity, and then you can watch them bend in a circular path. But sometimes the particles are already going fast, but some of them are going really fast, some of them are going moderately fast. And the velocity selector lets you pick out the ones that are going a certain particular speed. So that gives us the chance to build a mass spectrometer. Now, the mass spectrometer is a very common piece of chemistry equipment. Basically, you evaporate a material, and the vapors go into the mass spectrometer. And one way to set up the mass spectrometer is to have an accelerating voltage. Another way is to have a velocity selector like on the previous page. Either way, the mass spectrometer is formed out of a beam of particles entering a magnetic field. So we're going to start with the magnetic field. X, 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 X. And we'll put our beam in here. V initial. So this is the exact same velocity and magnetic field we had on the previous page. So the velocity is towards the top of the page, magnetic field is into the page, so our force is to the left. The difference is this time we're not going to have the electric force. So we're going to let the particles experience the magnetic force. F sub B. And when you have a massive object moving with a force perpendicular to the velocity, the massive object is going to change directions. And it's going to basically go in a circular path. And the magnetic force isn't going to change the velocity or the speed of the particles. It's just going to change the direction of the velocity. So now we're going to have F net equals ma, and this is going to be qvb because the only force is the magnetic force. And this is going to be, the acceleration is v squared over r. And then that gives us r is mv squared over qvb equals mv over qb. So if you send your particles into the mass spectrometer with all the same velocity, and they all have the same Q, and they all have the same magnetic field because you made the magnetic field, then the radius of the curve is going to depend on their mass. And the ones with more mass are going to take bigger, broader circles, and the ones with less mass are going to go in little tighter circles. And you'll effectively separate the beam into a beam for, say, molecular mass 18 particles and a different radius for molecular mass 32 particles, et cetera, et cetera. So you can separate the different molecules of your mixture and then measure how much of each one you have.
So for this, like we did today, we calculated, like we want to calculate the radius of a proton. When we're doing that, if it was like, if you give us a question like a certain amount of protons, do we add them together or just go off the one, like with the masses? Or does that not make sense?
It's for each particle.
That's for each.
Yeah, because if you had multiple protons, you could combine them together to get extra mass, but it would also have extra Q. And the extras would cancel in this fraction. So twice as much mass built out of protons would have twice as much Q. In the mass spectrometer device, you have different amounts of mass, but every single molecule has one electron stolen from it. So the Q is E, the elementary charge. But if you thought of a clump of like 4 protons but nothing else, then it would be 4 times as much mass, but also 4 times as much Q. Yeah.
This one that are in that radius, what was the technical term for it? Is the term?
It's the cyclotron radius, I think. Yeah. I think that's the name for it. Yeah. Apparently don't have an example put together for this. But there is at least one question on the homework that, that I finally got put together fairly recently, so I set it to be due next week. The homework 3. Now I want to talk about, real quick, the other 2 effects on, well, I should form a sentence before I start the words. Otherwise, I get halfway through and realize I started wrong. I want to talk about the other way of calculating magnetic force and one of the other effects, which is magnetic torques. All of the third effect, which is induced voltages, I don't want to talk about today. So, force on a current. So this is F sub B is equal to I times the length times the B times sine theta. So in this case, it looks very similar to the previous formula. Compare F sub B is equal to QVB sine theta. It's just that an amount of current and the length of a wire are taking the place of the Q and the V. And they actually have the same units because current is charge per unit time. And if you take charge times length per unit time, that's the same as taking charge times length per unit time. So the units are exactly the same, and the formulas are exactly the same. Now this is kind of significant because this used to be the way, actually it might still be the way that the ampere is defined. I think it still is the way that ampere is defined. That our elementary unit of charge of 1.6 times 10 to the minus 19th coulombs, that depends on knowing how much a coulomb is. And knowing how much a coulomb is turns out to depend on knowing how much an ampere is. And this force B is actually used to define how big an ampere is. And that's used to calculate the force between two currents. Now, this use of the word between means that this is a force that the two currents exert on each other. Remember when we did Coulomb's law, we talked about like charges repelling, and we said that the force was KQQ over R squared, and if the charges are the same, then it's a repulsive force. And the one feels a force to the right and the other feels a force to the left. So that's the use of the word between here. So let's draw up a situation and calculate some amount of force. So we're going to have I1 equals 2.0 amperes. And then I just want this to be the line. We're going to have I2 equals 0.3 amperes, two different amounts of current. Now this one is going to be the source, and this one, I call it the object. So the way we would do this calculation is first, we figure out what the source does. The source is a current, so it's going to generate magnetism. So we need to figure out the magnetic field due to the source at the location of the object. So the source has a current that's heading to the right. It's our thumb. The magnetic field curls around it by the right-hand rule. So it comes out of the page up there into the page down there. So down here at the bottom, we're going to have a series of dots, X's, into the page. So B1 is, and we look up one of our formulas for magnetic field. Now this I1 is a long straight wire, so we look up the magnetic field of a wire, and I've done this enough times that I remember it. It's mu naught I over 2 pi r. I guess I need a distance. Let's make this distance 0.6 meters.
So you're saying that these currents they're perpendicular, they're not parallel?
The currents are parallel to each other. They're going side by side. Both currents are pointing in the x direction.
Why are the X's? They're
The-
curving from
The
top to
x's
bottom.
are created by the source. So it's coming out above, down the front, and into the page there. And the second current is kind of bathing in a region where the magnetic field is pointing into the page. And we're calculating now the strength of that magnetic field. And this would be 4 pi times 10 to the minus 7th times our 2.0 amperes over 2 pi times 0.0, I'm sorry, not 0.0, just regular 0.6. So this would be a value. I get 6.67 times 10 to the minus 7th Teslas. Not a very strong magnetic field at all. Weaker than the magnetic field of Earth. This would be a terrible experiment. Now we can calculate the force. So now we go to our right-hand rule, just thinking about I2 and its magnetic field that it feels. So the IL, the current takes the place of our QV. Magnetic field is into the page. It feels a force that's upwards. So this is F sub B is lifting upwards on that other wire. And then the strength is F sub B is equal to ILB is 0.3 amps times L times 6.67 times 10 to the minus 7th Teslas. And one way to think of this is as a force B per meter is equal to, so just divide both sides by L, and we get a force per unit length. And we get 2 times 10 to the minus 7th newtons per meter. And that's not rounded anymore, because the way I concocted this, the 0.6 kind of ended up dividing up with the 0.3. And then over here, the pi's can actually be canceled. And something like this is used to define how big the ampere is, basically saying if you have two wires that are 1 millimeter apart, then a force of 1 Newton per meter is generated by a current of like 1 milliampere or something like that, or 1,000 amperes. I forget which way it is. I haven't worked on that definition in a long time. But I could calculate it if I had to. One of the weird parts of this is it doesn't really follow our general rule of opposites attract. Because here we have like currents. Both currents are heading to the right, and they appear to be attracted together. And that's true. So just as the lower current is pulled upward, the upward current would be pulled downward. So these two parallel currents would be attracted together. And then the opposite is also true. If they're in opposite directions, then they're repelled apart. So this is like the one violation of our opposites attract and like things repel rule. All right, one more thing. I want to calculate a magnetic torque. And this is basically how we turn magnetism into motion. So first, I'm going to draw some bar magnets here. So there is bar magnet there. And there's a bar magnet there. And this one is going to have a north there, and this one's going to be a south. So I haven't drawn the rest of the bar magnets. Maybe this is a big, like, circular magnet with a gap in it, or maybe it's just there's a magnet there and there's a magnet there, and this is the back of the magnet, which would be a south over here. But what I do know is that the north should emit magnetic field and the south should suck in magnetic field. So that means that in between here, I'm not going to draw it the whole way across because I need some space in there to draw the rest of the thing. We're going to have magnetic field pointing that way. Now, what are we going to put in there? We're going to put a loop. So I'm going to draw an axle. And then have that axle meet up with a square loop like that. Yeah. And we're going to have some current go around in that loop. So the way this is drawn, there are 4 segments to the loop. And let's look at the magnetic force on each one of those. So B equals right, I equals out, because the top segment of the loop has the current coming toward us in my pseudo 3-dimensional drawing here. So I want to figure out the direction of the force. Current's coming towards me. B is to the right. That makes my thumb point up. It also gives me a wrist cramp. So this is F sub B equals up. Current is positive. Yeah, you draw the current in the direction of flow of positive charges. Yes. Front segment. So in the front segment, I is down. So FB is, I is down. Magnetic field is to the right, so FB is out of the page. The bottom segment, I equals in, FB equals down. If I reverse the direction of the current from the top segment, then I'm going to reverse the direction of the magnetic force. And the back segment, I equals up, FB equals in. So basically, each of the four sides of this square is going to feel a force kind of pulling it away from the square. And that's not going to cause a net torque because each of those forces is directed through the center of the square. But what it does do is it provides a preferred direction for the loop. This loop is happy to be in this direction. So it will not spin on the axle. So that's the axle, is that line that goes in and out of the page. But what if we turn the loop slightly from its orientation? And I think what I want to do here is copy and paste a drawing that I drew before, because I don't want to take, I only have a couple more minutes. So there we go. So there's a new version of the drawing. It's going to come up in a second. So in this version, the dot here represents the current coming out of the page. That's the top segment of the loop. The X here represents the current going into the page. That's the bottom segment of the loop. And what we've done with the loop is, instead of having it be a square facing up and down, we've turned it slightly. And this force, due to magnetism on the top segment, is still going to be straight up. And the force due to the bottom segment's interaction with the magnetic field is still going to be straight down. And that's going to tend to try to pull the loop back into its previous orientation, where the current was going out of the page, straight down the front, into the page, straight up the back, out of the page, straight down the front. So the tilted loop will try to go back to its previous orientation. So So it feels a torque. An attempt to move something in a rotation is a torque. And I'm going to write down the formula just because you'll need it for your homework. And we'll probably start with talking about this again on Wednesday. I like this version of the formula because I can remember NBA because I don't like basketball, so it stands out to me. I don't know. And N is the number of loops of wire. A is the area of the coil. And theta is measured like this. It's the angle between the magnetic field and this vector I've labeled n hat. The hat stands for direction and n stands for normal. And this is a normal vector for that particular loop. And if the loop is twisted so it's vertical again, then the normal vector would be aligned with the magnetic field and then there would be no torque anymore. So we'll talk about how to use this equation then on Wednesday. Yeah.